Electric generators are important devices in our daily lives because they provide a reliable source of electricity for homes and businesses. They work by converting mechanical energy into electrical energy through rotational motion driven by energy sources such as wind, water, steam, or internal combustion engines. To understand how they work, we need to explore basic concepts like electromagnetism and the electromagnetic induction principle. Let's start by looking at how an electromagnet works. When an electric current flows through a coil of wire, also known as solenoid, it creates a magnetic field around the wire, turning it into an electromagnet. Inside the solenoid, the magnetic field lines are straight, evenly spaced, and all point in the same direction, just like the magnetic field of a bar magnet. You can determine the direction of the magnetic field produced by a solenoid using the right-hand rule. If you hold the coil with your right hand and your fingers follow the direction of the current, your thumb points in the direction of the magnetic field. Changing the direction of the electric current will change the direction of the magnetic field. When the flow of electricity is stopped, the metallic wire will lose its magnetism and return to a normal state. This is the basic principle of how an electromagnet works. An electromagnet shows that an electric current can create magnetism in a metallic wire. But can the reverse also be true? Can a magnet create electricity in a metallic wire? Michael Faraday, an English scientist, discovered that when the magnetic field surrounding a metallic wire changes, it can create an electric current in the wire. This discovery, known as Faraday's law of electromagnetic induction, is essential for how generators work. Electromagnetic induction can be demonstrated with a device called Faraday's iron ring, which consists of a soft iron ring with two separate coils of wire wound around it. When the current flows through the primary coil, it becomes magnetized just like a solenoid. This creates a sudden increase in the magnetic field's strength, which induces a momentary current in the secondary coil. When the current in the primary coil stabilizes and the magnetic field remains constant, no current flows through the secondary coil. When the current stops in the primary coil, it gets demagnetized, causing a sudden decrease in the magnetic field strength, which induces another momentary current in the opposite direction in the secondary coil. This experiment demonstrates that a magnet can induce an electric current in a wire only if there's a change in the magnetic field. Let's examine an alternative scenario in which a wire can experience a change in the magnetic field. Consider a situation where the magnetic field remains constant, but a wire is in motion relative to a permanent magnet. When the wire moves vertically, parallel to the magnetic field lines, no current will be generated because the magnetic field does not change relative to the wire. Similarly, no current will be induced if the wire is moved horizontally, as the magnetic field does not change relative to the wire. However, when the wire is moved perpendicular to the magnetic field, crossing the magnetic field lines, it encounters a change in the magnetic field, leading to the flow of current through it. This demonstrates that current is only generated when the wire intersects the magnetic field. Now that we understand the basics of electromagnetism and electromagnetic induction, let's see how these concepts work together to create a generator. The generator is a device comprising a coil of wire situated within the magnetic field of a permanent magnet. The coil is connected to a wind turbine through a shaft, providing the continual mechanical force required to rotate the coil. Each end of the coil is linked to a separate slip ring that rotates along with the coil. The white side of the coil is connected to the white slip ring, and the black side of the coil is connected to the black slip ring. These rings maintain continuous contact with fixed brushes, which are connected to a light bulb circuit through wires. When wind energy turns the turbine, it sets the wire coil in motion, causing it to rotate in a clockwise direction within a magnetic field generated by a permanent magnet. As the coil moves through the magnetic field, it creates an electric current. The direction of this current can be determined using the right-hand rule. By pointing your right index finger in the direction of the magnetic field and your thumb in the direction of the coil's rotation, your middle finger will indicate the direction of the current. During this process, the current flows upward on the black side of the coil and downward on the white side. As the coil reaches the vertical position, the change in the magnetic field ceases, resulting in the absence of current flow. When the coil completes half of a full circle within the magnetic field, the current's direction changes. Following the right-hand rule, the current flows downward on the black side and upward on the white side. Once the coil returns to the vertical position, the current stops flowing, and the cycle repeats. Because the current changes direction every half cycle, this type of generator is called an alternating current generator. To convert an AC generator into a DC generator, you can modify the generator's structure by replacing the slip rings with a commutator. This commutator comprises a split ring and plays a crucial role in altering the direction of the current. When the coil within the generator completes half a circle, the brush's connection with the split rings is reversed at the precise moment when the current changes direction. As a result, this mechanism ensures that the current consistently flows in one direction within the circuit, transforming the generator's output from AC to DC. This is how electric generators generate electricity, which is then added to the power grid for distribution. If you enjoyed this video and want to see more like it, please subscribe to this channel. Thank you for watching.